Well, good morning. Last lecture, what we did, we developed this inverse operator for first order low pass inverse operator and for Heaviside operator. So, and what we did essentially was to look at this differential equation, y prime plus ay equals x of t. So, and we noticed that you can also write this in terms of the Heaviside operator as p plus a operating on y producing x of t. And we said that if there's an inverse for this compound operator, and we show it as 1 over p plus a, we demonstrated that you can actually do it this way. You can solve it. I mean, if you apply the inverse operator, obviously you can produce y of t. And what we did, we calculated what this inverse operator was. And we showed that inverse operator to be e to the negative at 1 over p, which is the integration from negative infinity to t, e to the at x of t. So we we showed that. And we showed that you can actually use this to solve differential equations. For this one is obviously solving a first order differential equation. And you can also write this, again, I'm rewriting what we did last time because it's important. It's in a less compact form of the same thing. Yes? Isn't the 1 over p supposed to be dropped? Yes. Thank you. Yes, I don't need the 1 over p because this is the 1 over p, e to the negative at. Thank you. So that's what that means, that 1 over p means. So that was what the inverse low-pass operator. And we also developed the inverse high-pass operator. We saw the high-pass operator. And by using the combination of the two, what we noticed is that actually these behave algebraically. And what that enabled us is to use these in the context of impedance and admittance operator, which we had talked about briefly before, but we can also kind of to refresh your memory. In general, if you have let's say a two-terminal thing, which may have inductors and capacitors and resistors, and they can be connected in funny ways to each other. As long as you have these two terminals, there's a relationship between this current and this voltage. So it's a compound branch, one branch made of some elements inside. We can say that as long as these are made out of lumped elements, you can actually relate these two through, for example, v of t can be calculated by applying this operator zp on I of t. Right? This is what we call the impedance operator. So it's an operator. And then you had the admittance operator, which is the inverse of that, which would be y of p operating on v of t generating I of t. So this is the admittance operator. And in this case, this is pertaining to one branch, but we can actually even generalize it. So what we can do, you can even have a circuit where it has an input, for example. We showed one example last time. I'll show you a couple more examples this time. So let's say you have a input Vs or Vin of t. And you're interested in looking at some particular voltage V out of t. And we can actually even express these in terms of an operator. In other words, we can define V out, or we can show V out in terms of an operator H of P operating on V in of t. So this is an operator operating on a time domain input, producing another time domain output. And this operator can be calculated in an algebraic way as long as these are lumped elements. So how do we do that? Well, one of the things that we notice is that we know the impedance and admittance operators for capacitors and inductors, right? For a capacitor, for example, the operator, the current, for a capacitor, the current I of t is Cp V of t. And inversely, V of t, so this is for a cap, is going to be 1 over Cp. We compound it by saying essentially it's 1 over C times 1 over P operating on I of t. And likewise for an inductor, what you have is that V of t is Lp I of t, and I of t is 1 over Lp V of t. So what this does, and of course you know what these are, right? I mean, this is basically equivalent to saying V is equal L di dt This is like saying I equals C dV dt for a capacitor, etc., etc. Right? That's a shorthand notation for that. But this combined with the fact that at least for these elements, these behave algebraically, then you can actually, it has an important corollary, which is that you can, if you have inductors and capacitors in your circuits, you can actually treat them like resistors whose values are these basically operators, CP, 1 over CP or LP. And we did one example last time which looked like this. I believe something like this. So you had a resistor, inductor, capacitor, resistor, and we are interested in this voltage as the V out. And what we are really interested in writing is writing V of t in terms of some operator operating on Vs of t, producing that output voltage, right? And the way to do it is that we said, okay, look, because of that relationship, this is simply, you can think of this as a resistor whose value instead of being R is LP, and you can think of this as a resistor whose value is 1 over Cp, or a conductor whose value is Cp. And if you do that, then essentially you can think of this or treat it like a resistive network and do whatever you did for the resistive network. So in this case, we did it last time, so I'm not going to redo it. I believe V of t was 1 over 2 plus RC plus L over R P plus LC P squared, operating on V of t. So we did this from last time. Yes?
If we change all of our inductors and capacitors into essentially being resistors, can we do source transformations with them, with those values?
If we change all of our inductors and capacitors into, I wouldn't say that change them to a capacitor or to a resistor. I would say treat them like resistors of this value. But okay, so what do we do? What's your question then, second part?
Yeah, can we do source transformations?
Can we do source transformation? Yeah. You mean with these sources?
Yeah, like let's say you switch the resistor and the inductor. Could we turn that into a Thevenin equivalent?
Oh, okay, that's a good question. So you say, can I take this? So you say the question is that can I do Thevenin equivalent, for example? Can I take this, right, and convert it to a Norton equivalent? You could, with the following caveat. So if you do this, then your source also need to have an operator operating on it. So this becomes LP. But remember, how do you get this current off of that voltage? So now you have to have 1 over LP operating of V of t. So your input current, whatever it was, would be the integral, 1 over L of the integral of that voltage.
So if it's DC, then it would end up just going to 0?
If it's DC, no, it won't go to 0 because it's an integral, right?
Oh,
Yeah, it becomes like, yeah. So something like that. I mean, so it becomes a different source, right? So if your source was, let's say for the sake of argument, if your input was a step, then this, to be equivalent of that, needs to have a ramp scaled with 1 over L. Right? So you have to think about this as really operators operating on things. So you have to be careful about that. I guess that's the point. But you can deal with it as long as you're careful and consistent. But anyway, let's continue. Okay. Any other questions before I continue? All right. So that was so this is some sort of a what we call the transfer operator or system operator. So these are what we call system operator. Sometimes we call them Heaviside operators, and that's what H stands for. And you will see a lot of these things, this system. And these operators become system functions and transfer functions and things of that sort eventually. We'll see that. So now one interesting question is that what is the order of the differential equation describing this system, this input-output transfer operation? It's second order, right? Because you have a p squared here. So it gives you a second order differential equation. Now, Could we tell that by looking at the circuit itself before we even started doing anything, before we wrote any math? How could we tell that? Is there something in the circuit that tells you 2? Yes?
I mean, the fact that you have like both an inductor and a capacitor, and like the inductor acts like a, basically they act like one acts like a derivative, one acts like an integral.
So the fact that I have an inductor and a capacitor and one acts like an integration and one acts like a differentiation, that's your response, right? That's one way to think about it. But how do we deal with these things in general? I mean, what is the what does the order of a differential equation tell you about the number of natural frequencies or the number of solutions? Well, if you have a differential equation of nth order, you can essentially have different natural frequencies in a way, right? And what are the natural frequencies related to? Natural frequencies of a system are related to what? It's a physical concept, if you will. It's how many, go ahead.
Frequency response.
Well, that's a result of that, but there's something even more fundamental. If I give you a mechanical system, an electrical system, a chemical system, a financial system, anything, if I want to know how many natural frequencies I should expect in the system, what should I look at? It means how many really independent knobs do I have in the system? How many things are there that I can set independent of each other, right? Another way to say that, a more exact way of saying it in this case, or others generally in differential equations term, is that how many initial conditions you can define independent of each other. So that's the way you can determine how many degrees of freedom you have. The most important thing to think about is degrees of freedom. Right? How many degrees of freedom you have, right? If you look at my arm, for example, if you forget about my wrist and hand, right? How many degrees of freedom do I have with my elbow? How many numbers do I need to describe what the status of my elbow is, the state of my elbow is? 1, because I can't really twist my elbow, right? Right? My elbow by itself, so this is 1 degree. This is 1 angle, right? I mean, if I have this 1 angle, that's 1 degree of the freedom that determines from a mechanical standpoint where my elbow exactly is with respect to, let's say, my forearm with respect to my upper arm, right? So now how about my shoulder? If you think about it, how many degrees of freedom do I have? I have this, and I have this, and I have this, right? So I can define 1 angle here, 1 angle there, and 1 angle here, right? I can define these 3 within reason, independent of each other, right? I can't go through the entire range. It will look very funny. It will be very painful. But within a certain range, there are 3 numbers that I need to use to describe the status of where my shoulder is. But with my elbow, I have. So the combination of these 2, how many degrees of freedom do I have? 4 independent degrees of freedom, right? So a differential equation describing these 2, if it was just had this and that, would be 4th order, for example. I mean, just as a very rough. I mean, there are a lot more subtleties and details and things of that. So it's a system like that. But anyway, so here, how many degrees of freedom do we have? How many to understand the degrees of freedom, you have to see how many independent differential initial conditions I can define. So I can define a voltage on this capacitor. I can say this voltage can be 3 volts. No contradiction will result, right? I can define this current to be 4.5 amps. No contradiction results between these 2 either. So I have 2 numbers that I can define independent of each other. So there are 2 degrees of freedom, right? There are 2 energy storage elements that can be defined, whose state can be defined independent of each other. All of these things are related to each other and essentially different ways of thinking about the same thing. The number of degrees of freedom, the order of the system, the natural frequencies, the number of energy storage elements that are independent of each other, etc., etc. They're all one thing, really. The problem is that many people don't see enough examples of different kinds to interpolate them and just like collapse them into one thing. And you should. So anyway, so you could tell up front by looking at this, because I can define 2 initial conditions independent of each other, that this is a 2nd order system. Any questions? Let's do one more example of these. This is also an interesting one because, generally speaking, if you want to teach somebody something, don't start with the pathological cases, but show them a couple of standard cases and then show them the pathological cases for them to understand the subtleties and how it should really be exactly applied. So this is a little bit of a pathological case, but it's something that happens quite a bit. And again, the same criterion still applies to it. So let's say this is the circuit that you're interested in. So this is Vs. You have two resistors here, R1 and R2, and then two capacitors. Let's do it this way. C1 and C2. And this is V of t, V out, what you're interested in. So this is your input, this is your output of the circuit. You can define this as ground to make your life easier. So we will write the transfer function of this based on the same method soon. But before we do that, let's talk about, let's apply what we talked about. What is the order of the system? What do you expect the order of the system to be? So I see people saying different things. So raise your hand if you say the order of the system is 2. Okay? Raise your hand if you think the order of system is anything other than 2. Okay, what is it if it's not 2? 1. Okay, some people are saying 1 and some people are saying 2. Okay, mission accomplished. So, the point of this thing is that this is at least something that's not obvious. Something that's not obvious and surprises you, that instead of getting upset at it, you have to say, what can I learn from that? When something surprises you in life, this is generally true. It means that something in reality does not match the model you have for reality in your head. Okay? A behavior of someone surprises you, the way certain things happen, the way certain system behaves. And the correct reaction is to go and correct and find out what is the model in your head that gave you the wrong result. What was wrong in that model and correct that model. There's also a second reaction to it, which is also interesting, which is going to try to change that thing or fight it. Sometimes it works. There are things you can change. And you should not dismiss that. But there are things that you cannot change, like physics. Okay, so here's the thing. So why do you say 1? Some of the people who said 1, why do you say 1? See why they would say 2, because there are 2 capacitors here. And you said, I can see what. Yes?
The 2 capacitors' voltages are also dependent on the source voltage.
Right. So, meaning, so we said the criteria was that can I really define 2 independent initial conditions? So if this, can I arbitrarily define this to be 1 volt and this to be 2 volt? 2 volts? Okay, what happens? What's the contradiction? If I define this as 1 volt and this as 2 volts, I have an ideal voltage source here. So you're saying what the voltage across this ideal voltage source is. And since it can't be all of the different possibilities that I can choose, there's a contradiction. It will have some value. You may say, what if it's 3? Okay, if it's 3, I can choose. I still may try to choose this to be 2 and 4. And that would cause a contradiction. So I really don't have 2 independent degrees of freedom. I only have 1. Although I have 2 independent energy storing elements. Right? So you shouldn't be fooled by the number of energy storing elements. You have to really see which ones are independent from each other. Yes?
So are we assuming we know C1, C2, R1, and R2, or are we saying that we can make those be whatever we want?
They can be whatever they want. But what I said has nothing to do with the value. You've got to be careful. What I said is about the initial condition, which is different from the value. This capacitor can be 2 farads. And its voltage can be 52 volts. These 2 are 2 independent things. But when we are talking about initial conditions, we are talking about these, not that, not the value component. So they are 2 different things. Shouldn't be, not to be confused with each other. Any other questions? All right, so let's find the transfer function. I'll employ your help in doing that. So we can treat them like as 1 over CP1 and 1 over CP2 if you think about them as resistors, right? And what we are trying to, so if you had this resistive network, how would we find the transfer function? If you had 4 resistors like that, how would we go about that? Well, this time let's start somewhere in the back. Yeah. So how would I go about solving this or finding this voltage in terms of this voltage if these were resistors? If this was R1, R3, R2, R4, whatever. Right, so you have a voltage divider, right? Which would be what? This equivalent resistance divided by the sum. No. So for example, a voltage divider. So if you have, think about this. If this is V1 and this is V, if this were Vs and V, if this was R1 and R2, how would you calculate V in terms of Vs? What is V in terms of Vs? V is Vs times what? R1 plus R2, right? So now this is the new, this whole combination is the new R2, and this whole combination is the new R1. So we need to calculate those. So we have a parallel combination of 2 things. How do you, what is that? To calculate this part of it? So this thing and that thing. Okay. So you are basically trying to calculate R2 parallel 1 over C2P, right? Which is the product divided by the sum. You can write it that way. So this is basically R over C2P divided by R plus 1 over C2P, which you can also write as R over 1 plus R. Well, this is R2. R2 C2P. So that's this equivalent impedance, really. And what is that one? By same token or by same, by symmetry, again, same thing, right? So it's R1 parallel 1 over C1P, which is going to be what? C1P, exactly. And what is the transfer function? So what is V in terms of Vs? So we have to apply something, right? Yeah, an operator in front of it, which would be what? This one divided by the sum of the 2, right? This is that new R2, or this is the sum of the 2. So I say R2 divided by 1 plus R2 C2P over R1 plus 1 plus R1 C1P plus R2 1 over R2 C2P. Operating on Vs of t. This is an operator, don't forget. We apply it from the right. I'm sorry, from left. From left. So we can simplify this a little bit, right? We're treating it algebraically. So you have a common denominator, so you can write it as, in the numerator you will get R2, 1, C1P, and in the denominator you get this times that plus this times that. So you get R1 plus R2 plus R1, R2 times C1 plus C2P, operating on Vs of t. So this is the new H of P. What is the order of this thing? Right? The order of the denominator is the order of the system, right? The order of the differential equation. Because this is the one that operates on this if you wanted to write the differential equation. Right? The denominator times that, or operating on that. So what is the order? What's the order? 1, right? It's first order. There's only 1p. There's no p squared. So you can also write this in a slightly nicer way. You can write as R2 over R1 plus R2, factor R1 over R2, 1 plus R1 C1P divided by 1 plus R1 parallel R2 times C1 plus C2P. These are somebody, late Professor David Middlebrook of Caltech was a professor here for, I think, a very long time, for 50 years or so. And he used to call these low entropy forms, because this is much better than that, because it shows you what the parameters, how the parameters affect each other. The usefulness of this thing is for design, if you want to design something based on this. And if you put it in, so what it says is that it's basically this resistive divider, if you think about it. This is that resistive divider. Times some dynamics, that if P was not there, which means that you're looking purely low frequency, right? If you set P to 0, it means that no height, no dynamics exist. Everything is static. So this becomes 1. So if you just ignore all the dynamics, if you're looking at it at DC, this is what it would do. It's basically simply that resistive divider. And this is where the dynamics is. So you separate this from that. This is what we call the low frequency gain. And this is what we call the dynamics, where the dynamics are. Right? So this is just a transfer function, so we can calculate. So if you wanted to now find what it is, you can apply these operators. If you want to plug some numbers in there, you can do that. And if you have some numerical things, you basically apply. This is simply what we had developed before. It's a 1 over P plus A, right? If you want to make it into one in exact form, P plus A, you need to factor this out, so it becomes P plus 1 over this thing. Right? And this is an operator. How do you apply this operator to V? If I told you what V of t is, let's say if I told you V of t is a step, what would you do with this? This is just a derivative, right? It's 1 plus this times the derivative of that. So it would be a step plus an impulse, for example, in that case. Scaled, the impulse scaled by R1C1. Right? So you should be able to handle it. I mean, of course, once you do more examples, this becomes more natural to you. So there's some interesting thing about this particular thing. This is not a completely contrived example. It's actually a very useful example. And this is used a lot. In fact, you will start using it, or you may have already used it, if you have used an oscilloscope probe. How many of you have ever used an oscilloscope probe so far? Okay, so you've seen how it works. Do you remember that? Have you seen this little, notice there's this 10x thing on it? It says 10x. Did you ever wonder what that is? What that is this. So let's say this is the oscilloscope. Knob. Switch. And then there's a input, BNC, cable coming in, going to something, your probe. There's a little switch here. There's a tip that you put on your board, or I don't know, whatever you have, your breadboard, etc., right? What happens is that is going to, so you're trying to sense this, right? You're trying to minimize the impact of what your oscilloscope does to your circuit. So you want this to be a good replica, the voltage that the oscilloscope sees to be a good replica of this. But this probe and this oscilloscope and everything, the oscilloscope input has some capacitance, right? So it has some input capacitance. You can't make something that has no capacitance. Now, if you just hook up this capacitance there, it will start degrading the signal, because if you're looking at something high frequency, it will just bypass it and filter it and reduce the signal. So it also has a resistor. So what you do, you intentionally, so you have it inside the probe, you have a resistor, and you intentionally add a capacitor. And then if you make this product, so now something interesting happens. So let's see. You have these two, so this is your R1, C1, and this is your R2, C2. So it does something very interesting. So you say, well, what is good about this? So let's see what's good about it. So let's say I wanted to get rid of this dynamics. Let's say I want to find out if there is a combination of R1, C1, R1 and C1 and R2 and C2 that would make this go away. Because that would be a good thing, right? Because then this voltage becomes an exact replica of this voltage. Except for the fact that it's scaled down by some division ratio. right? Can you come up with some values where this disappears? This dynamics becomes just 1, this whole bubble. Well, for this to become 1, what do we need to have? We need to have this being equal to that. Because then the numerator and denominator will be equal, they will cancel each other. Right? See if we can enforce that condition. So we are saying what we want is for R1 C1 to become equal to R1 R2 over R1 plus R2 C1 plus C2. Right? I multiply both sides by this, so I get R1 plus R2 here, get rid of that. So then I will see that I have an R1, R2 here. So let's write it out. R1 squared C1 plus R1, R2 C1 equals R1, R2 C1 plus R1, R2 C2, right? So these two cancel, right? And then these two have to be equal, so I cancel one of those R1, so I get R1 C1 equals R2 C2. So if R1 C1 times C1 is equal to R2 times C2, this becomes 1. So it acts like a resistive divider. So what you do, if you make this product the same as that product, and the way they do it, they make this 9 resistor, and they make this 1. So 9 to 1. Now 9 something, 1 something. The ratio is 1 to 1. Now what you can do by putting the right capacitor here, you can actually make this go away, make the effect of this capacitor disappear. And how do you do that? If you have used your probe correctly, so I'm going to ask at the end who has actually done this. There's a little thing on every oscilloscope. There's a little kind of piece of metal sticking out like a little bar of metal, right? You need to first calibrate your probe. The way you do it is that you attach it to this thing. This produces some sort of a square wavy thing. And there's a little knob or turn or a twisting thing. There's on different probes it's different on the probe. So when you hook it up to an oscilloscope, you will see a waveform. Now, sometimes when you hook it up, you see something like this. Sometimes when you hook it up, you see something like this. It means that the probe is not calibrated. You play with that knob till you get this square wave. And that means that at that point, this product has become equal to that product. And that's why your probe has a 10x, because you can see it's a 1 to 10 division. So all it does is just an attenuation of the voltage, but it's the better quality voltage, so you can always amplify it inside and make it look good, but you get the correct waveform. Anyway, so this is a useful thing. It's not a completely useless thing. But you can see that depending on what this capacitance is, it can be what we call an overshoot or an overshoot response or a damped response. All right. Any questions? Does this make sense? All right. So let's take it a little bit farther. Now, so I said, okay, fine. And some of you actually already have speculated about this before. But so if you have something like this, you can also apply the nodal analysis to it. Analysis. Revisit it. So now let's say you have a circuit. You remember when we were doing the nodal analysis, I said, when we come back to it, we can actually even do it, generalize it to inductors and capacitors and things of that sort. So this is when we are going to do it. So let's say you have something like this. So this is C1, this is C2, this is L, this is G, and I'm interested in this voltage, knowing this voltage. And I'm trying to perform nodal analysis on this. Can I do nodal analysis now, based on what you saw? How would you do the nodal analysis? Again, you treat these inductors and capacitors the same way that you treated your conductors or resistors, right? As conductances. So as conductances, what is this? What is the conductance of, or more accurately, the admittance of this component, this element, this capacitor? C1p, right? And this is C2p. And what is the admittance of this element? 1 over LP, exactly, right? So now if I think about these 4 components as conductances, I can exactly apply the nodal analysis the same way that I applied it before. So let's do it. Let's apply it. So let's do it together. So, and remember, now you can see why we were talking about Y matrix, because these are admittances, and admittances are shown with Y. We didn't say G matrix, because admittances are more generalized than conductances. So now we are going to write the Y matrix, because these are Ys. Okay, so let's write the Y matrix. I mean, we can even do it by inspection. We know the trick, right? So the Y matrix describes these voltages in terms of a stimuli current. So V1, we can call this V1 and V2, is expressed as a Y matrix. So for the first element, what do we write? So I guess who's next in line? So yes. How did we do the diagonal terms? All the conductances attached to the node, right?
So C1p. Oh,
Wait a second. Actually, there's something a little bit wrong with this. This has to be a current source. Why it has to be a current source? Because if it's a voltage source, this voltage is already determined, right? Yeah. No, my bad. No. So it should be IS of t. Obviously, just because it can be a voltage too, but then the problem becomes trivial, because then you know this voltage. It's a one node Y matrix analysis, which is a single calculation. So what is that? Okay, so now that we corrected my mistake, so what are the conductances attached to it?
C1p.
Okay, C1p 1 over LP. And what is the other element here? The 2 element? C1p? C2p? 1 over LP? Plus G. There's no 2G. Yeah, G. Yeah. And what are the off-diagonal elements?
The things they share.
The conductance they share with there's some caveat to that. It's about sign.
Oh, it's negative.
Yeah.
Negative 1 over LP.
Negative 1 over LP. Operating on IS of t and 0. So these are the equations describing the voltages of these 2 nodes. Now, in general, if I were to solve this equation, did I miss something? Did I miss something? So in general, so now how do I solve this? This is the Y matrix. So this is basically V equals Y matrix times IS, the stimuli vector, right? So now how do I solve this? How do we go about solving this? Yes, there seems to be a problem. Sorry, go ahead.
Shouldn't it be I equals conductance times V? Because you're saying V equals I over R.
Yes, I messed it up.
Just swap the V and the I matrix.
No, wait a second. Wait a second. Yeah. I made a total mess here. Thank you. Okay, so this is obviously this applied to my matrix V1 and V2 to produce IS and 0. Right? Thank you. Yes, so obviously this is applied to the voltages to produce the currents. So it's applying to V of t here. And then to solve the problem, obviously we need to invert it. So this is I, obviously, equals to Y V. And to solve this problem, what we need to do is obviously to write V equals Y inverse times IS. So now we need to invert. Thank you for that important clarification. Okay, so now what do we do? Well, how do we invert this? So we will, yes, continue.
Say, for
The first thing before even you get to the cofactors, you need to do something. Because we may be wasting our time if first we need to do what? Determinant. See if it can be inverted or not to begin with, right? And the determinant actually has the one that has a lot of information about this. We'll see. So what is the determinant of this thing? So the determinant of y is C1p plus 1 over LP times C2p plus 1 over LP plus G minus 1 over L squared P squared, which you can simplify as C1 C2 P squared plus, okay, so this is that one. Then this one gives you what? Plus C1 over L plus, let me stand on this side. And then C1G, C1P. This one gives you C2 over L. This one gives you what? 1. And this one gives you G over LP. No, this one doesn't give you 1. This one gives you what? 1 over L squared P squared. L squared P minus L squared P squared, right? So that's the determinant. These two cancel, right? So what we are left with is C1 C2 P squared plus G C1 P plus C1 plus C2 over L plus G over LP. So that's the determinant of the Y matrix. Okay? Good. So first of all, what is the order of this determinant? Okay, before you answer that, let's talk about the circuit. Looking at the circuit based on the criterion that we developed, what is the order of the circuit? How many different initial conditions can I define to independently? So how many of you say it's 4 or greater? Okay, good. Nobody. How many of you say it's 3? Okay. Yeah. All right. How many of you say it's 2? How many of you say it's 1? How many of you say it's 0? Okay. Good. All right. So now here's the question. Those of you who said it's 2, why is it 2? Anyone wants to tell us why it's 2? Yes.
I could be wrong. But
That's okay.
there's the voltage over
You are, but that's okay. It's okay. But go ahead. Tell me what your reasoning is.
the voltage over one of the capacitors and the voltage over the inductor. Oh, no, wait, the inductor.
No, the inductor is the current,
Yeah.
right? So that's the thing. So let's say 1 is if you set this to 1 volt, right? And if you set this to, I don't know, 5 volts, does it limit me in terms of what this current can be? Can I set this current to be 2 amps? Whatever, 5 amps, right? It's a current and a volt. I think what you were thinking is probably this, which is good that you noticed that aspect of it. If I had 3 capacitors, if I had this circuit, right? If I had this circuit, then now what's the order of the circuit? I want you to continue on that thought process.
I mean, I guess it's 2 now because
It's 2 now. Why?
the voltage over the right capacitor and the voltage over the
So let's say if I set this 2 volts and if I set this to 3 volts, can I set this to any arbitrary voltage that I want? No, right? What is the voltage? 1 volt, exactly. So what you noticed is correct in the sense that if you had 3 capacitors in a loop, you will run into that trouble. But you have to be careful here. When you have the inductor and the 2 capacitors, then what happens is They're not independent of each other.
So are the capacitors not independent of each other?
Well, so if they were connected directly, if there was no intervening element, connecting element. So let's say if this inductor was not here, if this was a wire, if I had shown two capacitors like that, what would the order of the system be? 1, exactly, right? Why?
Because they have to be the same voltage.
The same voltage. And if I set this to 2 volts, this is 2 volts. So it makes sense because that circuit really is this circuit. Right? Which is equal to this circuit. Does it make sense? Now I'm going to throw you another curveball, since you are on the subject. So what if I had kept my mistake? Well, it was not technically a mistake. It would have been a bad example. But now what's the order? With the inductor. No.
So would it then be 2 because the current of the inductor can be whatever it wants?
The current of the inductor can be whatever it wants, right? The current of the inductor can be 5 volts. And the voltage across the capacitor can be, I'm sorry, the current cannot be 5 volts. It can be 5 amps and 3 volts, right? Right? But how about the voltage across that capacitor? Can I set it independently, whatever I want? No, if it's a voltage source, if this became a voltage source, then that voltage source will tell me what this voltage is. I can't set it arbitrarily. So I don't have that degree of freedom. So this is interesting because when I have this as a current source, the order of the system should be 3. But if I have it as a voltage source, the order of the system would be 2. That's why it's important, because current source essentially is, you can think about it as an open source that has something added to it. Right? A voltage source is a short circuit that has something added to it. Go ahead.
So the answer is 3
Which one?
for like first question?
The very first one.
Okay.
Yes, the answer is 3. Is it clear why?
Isn't the current somewhat dependent on what IS of t is?
Sure, but it's not fixed by it because there's also this third current. That's actually, okay, so you asked another good question. Okay, good, no, good question. Here, if I take this out, now what's the order of the system? With the current source. 1, exactly. Why? For the reason you said, but please repeat it for everyone.
Because the current over the inductor is IS.
The current, it's a current source in series with an inductor. So can I set this to be 5 amps? No, because the current is forced by this guy. You can't change it. You have no degree of freedom to control it, right? So this is essentially now it's the order of 1. Okay. So I'm going to ask the class another question now that we are in the subject, because I think it's important to understand it. So now this is for everyone, not just Julie. So I took the brave one and I gave her all the hard ones. But here's another one. This is a tricky one. Think before you answer. What is the order of this one, this system? 3 inductors, like that. I want everyone to think. Raise your hand if you have your answer. Okay? Just one? Okay. It's okay to guess. It's all right. We all guess, and sometimes we're wrong and sometimes we are not. That's fine. That's better than not guessing. Yeah. All right. So who wants? Okay. So let's see. Somebody who has an answer today. Raise your hand. Kavya, do you want to go?
Guessing 2 because you know the current, or you can set the current across L1. Then once you get to the parallel circuit.
Okay. So let's say we set this current across L1 to 2 amps.
Right. So then
or 1 amp, just for the sake of argument.
So then it has to split into the parallel part?
Can I make this current like 5,273 amps?
I mean,
Well, is this allowed by something?
as long as the current across L2 is adjusted, so you only have 2 degrees.
Right. So far I haven't violated any law of physics, right? Or have I?
Yeah, I know it, or at least I think I thought about it. But the voltage across L1 and L2 still has to be V, which means that if we know L1, then we know, if we know the current through L1, we have to know the current through L2.
But remember, the current of the inductors and capacitors depend not only on their instantaneous voltage, but also the past. Because it's an integration and or differentiation, right? Does it make sense to everyone? Right? So if you know the voltage here, and this voltage here, doesn't necessarily mean that you know the current. This voltage can be independent, can be any value independent of the current. The same thing for a capacitor, the opposite, right? If I tell you what the current through this capacitor is, I haven't told you what its voltage is. I've just told you what the rate of change of voltage is. Yeah, I could be, if the current is 1 amp, this voltage at that instant could be 5 volts, it could be 2,753 volts, right? Any arbitrary value. Because its I is C dV dt, which means that V depends not only on the instantaneous value of the current, but also all of its past history. Right? That's the memory part of it. Okay, so now let's go back to this question, the question in hand. If this is, so can I define this to be 1 amp? No problem. Can I define it to be 5,273 amps? Still no problem. Can I define to be 33 amps? No. Right? It has to be exactly what? What is this current exactly? This current is exactly negative 5,272 amps. Right? KCL. If I make this anything other than this, then I've violated KCL, which means that I've violated conservation of charge and I've done bad things. If I set a capacitor voltage, 3 capacitor voltages in a loop to be, so if I make this 1 volt, 271 volts, and make this to 5 volts, I have violated KVL, right? Which means that I violated conservation of energy. That's the problem from a physical standpoint. So now here, so what was the answer to this question? How many degrees of freedom do I have? Independent degrees of freedom. 2. The 2 things I can define. I could define this and that, but that doesn't matter. I can define this to be 1 amp and 2 amps, and this would become basically negative 1 amp. Right? Yes?
So when you are saying defining these currents, are they instantaneous values, or are you saying that's the function of the current?
No, I'm saying that at any instant, can these 3,
Okay.
or essentially I'm defining the initial condition. I'm defining them, at an instant, and more specifically in our notation, it's a very specific instant. It's this instant.
Okay.
0, negative, not 0. 0 minus.
1/0.
Yeah, 1/0. Good. Yeah, so it's I of infinity. That's the infinite value. That would be a funny way to write it, right? If I want to say, oh, t goes to infinity, I can write it as t goes to.
Isn't that also negative infinity? 1/0 is plus or minus infinity.
Yeah, that's right. Yeah. I'm making it even worse. They say, when you find yourself in a hole, you've heard this expression, right? When you find yourself in a hole, stop digging. Okay, anyway. All right, so here's the thing. Let's go back to our example. So what is the order of this thing after all of this conversation? Again? 3. So what's the order of the determinant of y? Is it 3? Yeah, it is a third order system. If I set this to 0, what do I mean by 3? It means that how many roots do I have? If I set this to 0, if I want to solve this equation? What's the order of that equation? I have to multiply by, one way to find out what it is with some caveats, you have to multiply by LP, then you get a P3, P cubed, right? So it's a third order equation. So the order of the Y matrix is actually the order of the system. Even more importantly, and we'll see this later more formally, the roots, and we can even see it now, the roots of this are the natural frequencies of the circuit. So the determinant of Y matrix plays an important role. But anyway, so that's the determinant. Fine. So let's go back to continue solving this problem after 15 minutes of a 15-minute detour. And you thought you were off the hook. Okay, so let's go back to you. Yeah. So what do we do next? So cofactors matrix, right? So what is the cofactors matrix? Right. 1 over LPG. What is this? What is here? 1 over LP. C1P plus 1 over LP. 1 over LP. This really goes there and changes sign. This goes there and changes sign. Plus 1 over LP. And 1 over that determinant. So that's the inverse Y matrix. And then you multiply it by IS of t and 0 to get the voltages. Okay? So now what I'm interested in is really which voltage? What am I interested in? The output voltage, V, right? Which is V1 or V2? V2, right? So I basically take this and multiply it by that to get this. And the only remaining term is 1 over LP IS of t. So V, let's write it with a different color. V of t is going to be 1 over LP divided by the Y, the determinant of Y, which I can write as C1 C2 P squared plus G C1P plus C1 plus C2 L plus G over LP time operating on Vs of t, or sorry, Is of t. Right? So that is the system. And you can actually simplify it by multiplying by LP, numerator and denominator. So you get 1 over C1 C2 P cubed plus G C1 P squared plus C1 plus C2 over LP plus G over L. Okay? So now, what would I get? I get a third, well, again, sorry, Is of t. What do I get? Is a third order differential equation. And if I wanted to solve it, what do I need to do? Do I need to factor this third order polynomial? And one way to do it is just by applying those inverse operators in succession. Does it make sense? But the key point of this discussion is that really you can apply the nodal analysis the same way. You can do anything, essentially anything you did before with that. Okay, any questions? Sorry, what? Should 1 over? Yes. I should have multiplied by actually 1 over LP. So let's do that. Let me do that. So if it makes it simpler, L here, gets rid of this L, and then gets rid of that L. And you can see, first you can check the units to see if it's correct or not, right? I mean, thank you for that correction. So here you can see it's 1 over G, or it has units of R, right? Which times current should give you voltage. And this is 1 over C1P. And it has units of LP and CP, which cancel each other, and G, right? And this one is L C P squared. So 1 LCP squared cancels itself, so we are left with 1 CP, which is like ohms. Good? All right. Any questions on this? Can you apply it? You're ready to apply it. Okay. All right, let's take a break.